Hello, and welcome back to my channel. To conclude this tutorial, I'll introduce one of the most fascinating constants in mathematics, Euler's number. Along with 0, 1, I, and pi, this constant plays a fundamental role in mathematics. In fact, all of them appear together in Euler's identity, a topic we'll explore another time. Like pi, E is irrational, meaning it cannot be expressed as a ratio of integers. Its decimal expansion goes on forever without repeating. Moreover, E is transcendental, which means it is not the root of any non-zero polynomial with rational coefficients. Another remarkable feature is that E can be calculated in many different ways. In this video, we'll explore some of these methods as a summary of what we've learned throughout this tutorial. Although it bears the name of the famous Swiss mathematician Leonhard Euler, this constant was first discovered by another great mathematician, Jacob Bernoulli, while studying compound interest. But what is compound interest? Imagine you deposit $1,000 in an extremely generous bank that pays 100% annual interest. After 1 year, your money doubles. Now suppose the bank pays 50% twice a year. After 6 months, you have $1,500, and at the end of the year, you add 50% of that amount, reaching $2,250. You earn more because you reinvested halfway through the year. This is called compound interest, and it is given by the following formula, where R is the annual interest rate, and N is the number of compounding periods per year. Our example with semi-annual compounding would be calculated as this. Now let's calculate monthly compounding. And if we compound 10,000 times per year, as you can see, the result approaches E. This means that if we take the compound interest formula with R equals 1 and let N approach infinity, we obtain the formula for calculating E using this limit. Let's solve it using what we have learned so far. If we substitute N directly, we get the indeterminate form 1 raised to infinity, so we need to solve it in a different way. Let's call our limit L and apply the natural logarithm. We'll use the variable x instead of n, since x is the standard choice when working with limits. The logarithm can move outside the limit, and by the property of logarithms for powers, the exponent multiplies the log of the base. Rewrite the expression and divide by the reciprocal of x. If we replace x, we obtain an indeterminate form 0 over 0. This means we can apply L'Hopital's rule. So, let's differentiate the numerator and denominator. To compute the derivative of the numerator, we apply the chain rule. Let u be the expression inside the logarithm. The derivative of u is the sum of the derivative of the constant 1, which is 0, and the derivative of 1 over x. Using the power rule, this gives minus 1 over x squared. Substitute these results to find the derivative of the numerator, but do not simplify yet. Place everything into our fraction. Notice that minus 1 over x squared cancels out, leaving only this expression. When we substitute x, the limit becomes 1. Now we have a simple equation. Exponentiate both sides. Since e raised to the natural log is L, we conclude that L is equal to e. Thus, we have proven that our limit equals Euler's number. Before we continue, let's pause to talk about polynomials. A binomial is the sum of two terms, for example, a plus b. If we multiply it by itself, we get a polynomial of degree 2. Multiply that result again, and we obtain a degree 3 polynomial. Repeat the process, and we get degree 4, and so on. Look at the last result and check the exponents of a. They start at 4 and decrease to 0. Remember that any number raised to 0 is always 1. The exponents of b increase in the same way. Let's number each term from 0 to n. Notice how get the following pattern. Check all the polynomials, including the one of degree 0. Focus only on the coefficients, the numbers in front of the variables. When no number is shown, the coefficient is 1. These coefficients form Pascal's triangle, where each number is the sum of the two numbers above it, and the edges are always 1. How can we write a formula to find these coefficients? As you might guess, such a formula already exists. This is usually read as n choose k because it represents the number of ways to choose k elements from a set of n elements without considering order. The exclamation mark means factorial, which is the product of that number by all positive integers below it. For example, 4 factorial equals 24. To understand this better, imagine you have 4 books and want to choose 2 to take with you. According to the formula, there are 6 different ways to choose 2 books from 4. If you arrange all possible combinations up to 4 elements in a triangular pattern, you'll see that it matches Pascal's triangle. The example below confirms that the values in both triangles coincide. The final step is to combine all the terms into a single formula. Since this is a sum, we use summation notation. Each term is a coefficient multiplied by powers of a and b. Putting everything together gives us the binomial theorem. Let's try it with a polynomial of degree 3. First, expand the summation term by term. Looking at Pascal's triangle, the coefficients are 1, 3, 3, and 1. Finally, simplify to obtain our polynomial. Returning to Euler's number, let's consider this expression as a binomial of degree n. Notice that, once again, we are using n as the variable instead of x. Now, apply the binomial theorem to this binomial. Substitute a by 1 and b by 1 over n. Then simplify. As we saw earlier, the coefficients follow this formula. We know that k can be equal to or less than n, but never greater. The factorial of n means multiplying n by all previous integers down to 1. This includes n minus k plus 1, n minus k, and so on. But let's stop at the factorial of n minus k, because this contains all the remaining numbers down to 1. This factorial cancels, leaving this expression. This simplified form replaces the binomial coefficient in our expansion. Look at the fraction. The numerator has k factors, since it multiplies from n down to n minus k plus 1. The denominator also has k factors, because it is n raised to k. We can divide each term individually, separate the fractions, and simplify. Notice the pattern. It is a product of several factors, which can be represented using the product notation, similar to summation but for multiplication. Observe what happens as n tends to infinity. Each factor approaches 1. Therefore, returning to our equation and applying the limit, this fraction will tend to 1. As we have seen earlier, this limit tends to e. And that gives us another formula for Euler's number. And now for something completely different. Imagine a single bacterium. As you know, bacteria love to reproduce. So, let's say this bacterium divides into 2 after 1 hour. Each of those divides again after another hour, so now we have 4. If they keep dividing every hour, we'll get 8, 16, 32, 64, and so on. This type of growth is called exponential growth, and it's described by this equation, which uses Euler's number. This isn't just a math concept. It happens in real life, like the early spread of a virus or how information goes viral online. Of course, it doesn't last forever. Growth slows down as it hits limits due to factors like resources or behavior changes. But let's take a closer look at this formula. Y is the value of the variable at time t. Y0 is the initial value. K is the growth constant. In our example, Y0 is equal to 1. But what is the value of k? To find it, we use the value of y when t is 1 hour, which is 2 bacteria. Apply the natural log to both sides. Remember this property? This means k is the natural log of 2, since bacteria double exponentially every hour. So how does our example look? First, we apply the power property. Then, we use this log property for the expression inside the brackets. And we get this simplified form. We can interpret this as growth with base 2. The quantity doubles every time t increases by 1. K can also be negative, in which case it is called the decay constant. Take the example of a battery discharging. Initially, the battery has 12 volts, but after 24 hours it drops to 2 volts. Use our formula slightly modified. Apply the natural log, and then the log property discussed earlier to get the constant. Replace V0 by 12, Vt by 2, and T by 24 to get the constant. This shows that the voltage decreases exponentially with a negative constant, as you can see by the graph. Do you remember at the beginning of this video, when we talked about compound interest? It is given by the following formula, where R is the annual interest rate and N is the number of compounding periods per year. For simplicity, we considered R equals 1, meaning 100% interest. Now, let's consider a different scenario. We have an initial capital Y0 that grows at a rate k per unit of time. In other words, our interest rate is not fixed, it grows continuously over time. This means that after n compounding periods, the value after t units of time will be given by this equation. If the number of periods grows indefinitely, we take this limit. As we saw earlier, this limit is the number e, which can be written more generally as this. By substituting x, we obtain the exponential growth formula. Throughout this video, we've seen several ways to express e and its role in the exponential growth formula, concepts that appear everywhere in science, finance, and nature. I hope I have shown you why Euler's number and the natural logarithm are so fundamental to mathematics. This marks the end of this video and the conclusion of our introduction to calculus. These lessons should help you build a solid foundation for understanding limits, derivatives, and integrals. Thank you for joining me. If you enjoyed this video, give it a thumbs up, don't forget to subscribe, and I'll see you in the next series.